Functional groups made simple. Welcome. In this video, we are learning functional groups in organic chemistry without making it feel like random memorization. A functional group is the part of a molecule that usually controls what the molecule does. It affects naming, boiling point, solubility, and the kinds of reactions the molecule can do. The goal today is not to memorize every possible molecule. The goal is to learn how to spot the important pattern quickly. By the end, you should be able to look at a structure, circle the key group, and say whether it is an alcohol, ether, aldehyde, ketone, carboxylic acid, ester, amide, amine, or another common group. We will move in the same exam focus style as the naming video. First, recognize the group. Then naming and properties become much easier. Here is the reason functional groups matter. Two molecules can have a similar carbon skeleton, but if one has only carbon and hydrogen, another has an oxygen-hydrogen group, and another has a carboxylic acid group, they can behave completely differently. One might be mostly nonpolar, one might hydrogen bond, one might be acidic. That tiny atom pattern changes how the molecule is named, how it interacts with water, how strongly its molecules stick together, and where reactions happen. So when you see an organic molecule, do not stare at the whole thing all at once. First ask, what is the special group attached to the carbon skeleton? That is the shortcut that makes this topic easier. Before we start, here are the goals. First, you should be able to explain what a functional group is in normal language. Second, you should be able to recognize groups by pattern, not by guessing. Third, you should be able to separate carbonyl groups, because that is where a lot of students mix up aldehydes, ketones, acids, esters, and amides. Fourth, you should connect the group to naming, physical properties, and simple reactivity. This video is built for recognition before naming. If you cannot spot the group first, naming feels harder than it needs to be. The big idea is this. A functional group is the active pattern in the molecule. The carbon skeleton is the main body of the molecule. The functional group is like the badge that tells you how that molecule usually behaves. For example, if a molecule has an oxygen-hydrogen group attached to carbon, we usually start thinking alcohol. If it has a carbon double bonded to oxygen, we start thinking carbonyl family. If it has nitrogen attached in the right way, we might be looking at an amine or an amide. This is why organic chemistry is organized by functional groups. Molecules with the same functional group often share similar naming patterns, physical properties, and reactions. Most mistakes happen because students look at only one atom instead of the whole pattern. For example, seeing oxygen does not automatically mean alcohol. An ether has oxygen too. An ester has oxygen too. A carboxylic acid has oxygen too. The difference is where the oxygen is and what it is attached to. Carbonyl groups are another major trap. A carbon double bonded to oxygen is important, but that alone does not tell you the full group. You have to ask what is attached to the carbonyl carbon. Is it hydrogen? Is it another carbon? Is it oxygen-hydrogen? Is it oxygen bonded to another carbon group? Is it nitrogen? That one question fixes a lot of confusion. Use this workflow every time. First, look for heteroatoms. That means atoms other than carbon and hydrogen, like oxygen, nitrogen, sulfur, fluorine, chlorine, bromine, or iodine. Second, look for a carbon double bonded to oxygen. If that is present, pause and sort the carbonyl family before doing anything else. Third, ask what is attached to that carbonyl carbon, because that decides whether the group is an aldehyde, ketone, acid, ester, amide, acid chloride, or anhydride. Fourth, check for carbon-carbon double bonds, carbon-carbon triple bonds, and aromatic rings. This order stops you from jumping to the wrong answer too quickly. We start with hydrocarbons, which only contain carbon and hydrogen. An alkane has only carbon-carbon single bonds. An alkane has at least one carbon-carbon double bond. An alkyne has at least one carbon-carbon triple bond. An arene is an aromatic ring, with benzene as the most common starting example. These groups are important because they describe the carbon framework before we add oxygen, nitrogen, sulfur, or halogens. For a beginner exam, the fastest recognition clue is the bond pattern. Single bonds only means alkane. A double bond means alkane. A triple bond means alkyne. A benzene-style ring means aromatic. Halogen functional groups are usually shown as an R group bonded to a halogen. The halogens you normally see are fluorine, chlorine, bromine, and iodine. In beginner naming, these usually act as prefixes. Fluorine gives fluoro, chlorine gives chloro, bromine gives bromo, and iodine gives iodo. So if you see bromine on a carbon chain, you usually describe it as bromo with a number. The warning is that halogens usually do not become the main suffix in intro naming. They are important, especially in substitution reactions, but they usually behave like attached prefixes in names. Now look at oxygen groups, but do not just say it has oxygen. Ask what the oxygen pattern is. An alcohol has an oxygen-hydrogen group attached to a carbon. A phenol also has an oxygen-hydrogen group, but it is attached directly to an aromatic ring. That difference matters because phenols can behave differently from regular alcohols. An ether has oxygen between two carbon groups, so alcohol is carbon attached to oxygen-hydrogen. Phenol is aromatic ring attached to oxygen-hydrogen. Ether is carbon group, oxygen, carbon group. The fastest way to avoid mistakes is to look at what the oxygen is connected to on both sides. Sulfur groups are less common in a first pass, but they are still useful to recognize. A thiol, pronounced thiol, has a sulfur hydrogen group attached to carbon. It is similar in pattern to an alcohol, except sulfur replaces oxygen. A sulfide, also called a thioether, has sulfur between two carbon groups, so the quick memory is oxygen pattern cousin. Alcohol has oxygen-hydrogen, thiol has sulfur-hydrogen, ether has oxygen between carbon groups. Sulfide has sulfur between carbon groups. For this video, the main goal is just to recognize the pattern when it appears. Nitrogen groups depend on what nitrogen is attached to. An amine, pronounced umine, has nitrogen bonded to carbon and hydrogen groups without a carbonyl directly attached. Amines often behave as bases or nucleophiles in beginner organic chemistry. A nitrile, pronounced ny-trile, has carbon triple bonded to nitrogen. That triple bond is the main clue. A nitro group has nitrogen connected to oxygen atoms, usually written as nitrogen-oxygen 2 on the slide. The key is not just spotting nitrogen. The key is asking whether nitrogen is single bonded like an amine, triple bonded through carbon like a nitrile, or part of a nitro group. Now we get to the most important family in this lesson, the carbonyl, pronounced carbonyl. A carbonyl means a carbon double bonded to oxygen. This group matters because oxygen pulls electron density toward itself, so the carbonyl carbon becomes partly positive. That makes the carbonyl carbon an important reaction site. But here is the most important warning. Carbon double bonded to oxygen alone is not enough to name the whole functional group. You have to ask what else is attached to that carbonyl carbon. Hydrogen gives one pattern, carbon gives another, oxygen-hydrogen gives another. Oxygen bonded to a carbon group gives another. Nitrogen gives another. So every time you see a carbonyl, ask what is attached to the carbonyl carbon. Aldehydes and ketones both contain a carbonyl, but the attachment is different. An aldehyde, pronounced aldehyde, has a hydrogen attached to the carbonyl carbon. It is often at the end of a chain because the carbonyl carbon still has that hydrogen. A ketone, pronounced ketone, has the carbonyl carbon between two carbon groups. So the quick test is this. Does the carbonyl carbon have a hydrogen attached? If yes, think aldehyde. If the carbonyl carbon is attached to carbon groups on both sides, think ketone. Do not decide based only on the carbon double bonded to oxygen. Decide based on what is attached to that carbonyl carbon. This is one of the most common mix-ups. A carboxylic acid, pronounced carboxylic acid, has a carbonyl carbon attached to an oxygen-hydrogen group. In naming, the clue is often the ending OIC acid. An ester, pronounced ester, has a carbonyl carbon attached to an oxygen that is bonded to another carbon group. The difference is small visually but huge chemically. Acid means carbonyl attached to oxygen-hydrogen. Ester means carbonyl attached to oxygen-carbon. A beginner mistake is calling an ester an ether because both have oxygen between carbon groups. But an ester also has the carbonyl next door, and that changes the functional group. Here are three more carbonyl family members. An amide, pronounced amide, has nitrogen attached to the carbonyl carbon. This is different from an amine because the nitrogen is directly connected to a carbonyl group. An acid chloride has chlorine attached to the carbonyl carbon. An anhydride, pronounced anhydride, has two carbonyl groups connected through one oxygen. You do not need to master every reaction yet. For recognition, keep using the same question. What is attached to the carbonyl carbon? Nitrogen means amide. Chlorine means acid chloride. Oxygen between two carbonyls means anhydride. This cheat sheet is the carbonyl family in one idea. Start with carbon double bonded to oxygen, then sort by the group attached to the carbonyl carbon. If hydrogen is attached, it is an aldehyde. If another carbon group is attached on each side, it is a ketone. If oxygen-hydrogen is attached, it is a carboxylic acid. If oxygen-carbon is attached, it is an ester. If nitrogen is attached, it is an amide. If chlorine is attached, it is an acid chloride. If oxygen connects two carbonyl groups, it is an anhydride. On tests, this is one of the fastest ways to stop confusing similar-looking structures. Now connect this back to naming. In the naming video, the first major step was finding the boss functional group. This video explains how to spot those groups in the first place. Once you recognize the main functional group, you can choose the parent chain that includes it, number correctly, and use the right suffix or prefix. Alcohols often use the ending OL. Aldehydes use al, ketones use 1, carboxylic acids use OIC acid, esters use O8, amides use amide. So recognition is not separate from naming. Recognition is what makes naming possible. Here are 4 naming examples. Ethanol, pronounced ethanol, has an alcohol group, so the name ends in OL. Ethanol, pronounced ethanol, has an aldehyde group, so the name ends in al. Ethanoic acid, pronounced ethanoic acid, has a carboxylic acid group, so the name ends in OIC acid. Methyl ethanoate, pronounced methyl ethanoate, is an ester, so it uses the oat pattern. Do not start by memorizing the whole name. Start by highlighting the functional group. The group tells you the naming clue. Functional groups also affect physical properties because they change intermolecular forces. Alkanes are mostly nonpolar, so their molecules mainly attract through dispersion forces. Alcohols and carboxylic acids can hydrogen bond, which often gives them higher boiling points than similar-sized nonpolar molecules. Ethers can accept hydrogen bonds from water, but they usually cannot donate hydrogen bonds because they do not have an oxygen-hydrogen bond. Carbonyl groups are polar because of the carbon-oxygen double bond. The safe comparison rule is this: for molecules of similar size, stronger intermolecular forces usually mean a higher boiling point. Water solubility is a tug-of-war between the polar part and the nonpolar carbon chain. Oxygen and nitrogen groups can help a molecule interact with water. Small alcohols, small amines, and small carboxylic acids often dissolve better because they can hydrogen bond or interact strongly with water. But as the carbon chain gets longer, the nonpolar tail starts to dominate. That is why you should not say a molecule is water-soluble just because it has oxygen. Ask how polar the functional group is, and also ask how large the carbon skeleton is. Functional groups help predict where reactions happen. Alkanes and alkynes often react at their pi bonds, meaning the extra bonding in the double or triple bond is the reactive site. Carbonyl compounds often react at the carbonyl carbon because it is partly positive. Amines can act as bases or nucleophiles because nitrogen has a lone pair. Aldehydes are useful in substitution reactions because the carbon-halogen bond can be involved in leaving group chemistry. You do not need every mechanism yet. The main idea is that the functional group points to the reactive part of the molecule. Now pause and try practice. 1. There are 3 structures labeled A, B, and C. Your job is to identify the functional group in each one. Do not just look for oxygen and stop. Look at where the oxygen is and whether there is a carbon double bonded to oxygen. For A, ask whether there is an oxygen-hydrogen group. For B, ask whether oxygen sits between 2 carbon groups. For C, ask whether you see a carbonyl. Pause the video now, write down alcohol, ether, aldehyde, or another answer for each structure, and then move to the answer slide. Here are the answers. A is an alcohol because it has an oxygen-hydrogen group attached to carbon. B is an ether because oxygen is between 2 carbon groups. C is an aldehyde because it has a carbonyl carbon with hydrogen attached. Notice how the answer did not come from spotting oxygen alone. All 3 involve oxygen in some way, but the pattern is different each time. That is the exact skill you need for tests. Look at the atoms and look at what each atom is attached to. Practice 2 is about carbonyl sorting. Each structure has a carbon double bonded to oxygen, so all of them are in the carbonyl family. Your job is to decide whether each one is a carboxylic acid, an amide, or an ester. Use the one question from earlier. What is attached to the carbonyl carbon? Is it oxygen, hydrogen, nitrogen, or oxygen bonded to a carbon group? Pause the video and sort them before going to the answer. Here are the answers. The carboxylic acid has a carbonyl carbon attached to an oxygen-hydrogen group. The amide has a carbonyl carbon attached to nitrogen. The ester has a carbonyl carbon attached to oxygen, and that oxygen is attached to another carbon group. The important part is that all three contain a carbonyl, so carbonyl alone is not the final answer. The group attached to the carbonyl carbon is what separates them. Practice 3 connects functional groups to physical properties. The options are propane, ethanol, dimethyl ether, pronounced dimethyl ether, and ethanoic acid, pronounced ethanoic acid. Ask which one has the strongest intermolecular attractions for molecules of similar size. Think about polarity and hydrogen bonding. Which molecule can interact most strongly with other molecules of itself? Pause the video, choose your answer, and then check the next slide. The answer is ethanoic acid. Ethanoic acid is a carboxylic acid, and carboxylic acids are very polar and can hydrogen bond strongly. Compared with propane, ethanol, and dimethyl ether, ethanoic acid has the strongest intermolecular attractions in this set. Propane is mostly nonpolar. Dimethyl ether is polar and can accept hydrogen bonds from water, but it does not donate hydrogen bonds to itself the same way an alcohol or acid can. Ethanol can hydrogen bond, but the carboxylic acid group is usually stronger in this comparison. Stronger attractions usually mean a higher boiling point when the molecules are being compared fairly. This is one of the biggest beginner mistakes, thinking every oxygen-containing group is an alcohol. An alcohol needs an oxygen-hydrogen group attached to carbon. An ether has oxygen between 2 carbon groups. An ester has a carbonyl next to an oxygen bonded to another carbon group. So the fix is simple. Never identify a group from one atom alone. Oxygen is not enough. Look at the full pattern around oxygen. Ask whether there is hydrogen attached. Ask whether there is a carbonyl next door. Ask what is on the other side of the oxygen. Another common mistake is mixing up amine and amide. Say them carefully. Amine is pronounced umine, and amide is pronounced amide. An amine has nitrogen without a carbonyl directly attached. An amide has nitrogen attached to a carbonyl group. That carbonyl changes everything. So if you see nitrogen, do not immediately say amine. First check whether the nitrogen is directly connected to a carbonyl carbon. If it is, you are looking at an amide. A good memory clue is amide has the carbonyl sidekick. Here is the checklist to use before a test. First, circle heteroatoms, oxygen, nitrogen, sulfur, and halogens. Second, look for a carbon double bonded to oxygen. Third, if there is a carbonyl, inspect what is attached to the carbonyl carbon. Fourth, check for carbon-carbon double bonds, carbon-carbon triple bonds, and aromatic rings. Fifth, match the pattern to the functional group table. This is much better than staring at the molecule and hoping the name pops into your head. Use the same order every time. This mini table is the highest yield review. Alcohol means oxygen-hydrogen attached to carbon. Ether means oxygen between carbon groups. Amine means nitrogen group with no carbonyl directly attached. Aldehyde means carbonyl-carbon with hydrogen attached. Ketone means carbonyl between 2 carbon groups. Carboxylic acid means carbonyl attached to oxygen-hydrogen. Ester means carbonyl attached to oxygen-carbon. Amide means carbonyl attached to nitrogen. If you can sort these 8 groups reliably, you will fix a huge part of beginner organic chemistry confusion. Final recap. Functional groups are the patterns that control how organic molecules behave. They affect naming, physical properties, and reactivity. Carbonyl groups need special attention because they all contain a carbon double bonded to oxygen, but they are sorted by what is attached to the carbonyl carbon. The best strategy is simple. Circle heteroatoms, find carbonyls, inspect attachments, then check double bonds, triple bonds, and aromatic rings. Do not memorize randomly. Recognize the pattern first. In the next video, a good follow-up would be isomers or resonance structures, because those topics build directly on recognizing molecular structure.